Hello everyone and welcome back. My name is Mr. Kowalt, and in this video we're going to be going over this problem where we need to determine the temperature at which an uncatalyzed reaction will have the same rate as the catalyzed reaction at a particular temperature. So let's get into this. Okay, so in this problem, we're told a popular chemical demonstration is the magic genie procedure, in which hydrogen peroxide decomposes to water and oxygen gas with the aid of a catalyst. The activation energy of this uncatalyzed reaction is 70.0 kilojoules per mole. When the catalyst is added, the activation energy at 20 degrees Celsius is 42.0 kilojoules per mole. Theoretically, to what temperature in degrees Celsius would one have to heat the hydrogen peroxide solution so that the rate of the uncatalyzed reaction is equal to the rate of the catalyzed reaction at 20 degrees Celsius? Assume that the frequency factor A is constant and assume that the initial concentrations are the same. Okay, so there's a lot here, so let's unpack. So the first thing we need to hone in on is that the rates are going to be the same. So we're looking at an uncatalyzed reaction and a catalyzed reaction, and we're said, what temperature do we need to raise the uncatalyzed reaction so that the rates are equal to each other? So the rate of the uncatalyzed reaction is the same as the rate of the catalyzed. So let's write that down. So we want the situation to be that the rate of the uncatalyzed, so we'll put UC for uncatalyzed reaction, is equal to the rate of the catalyzed reaction. We'll put C for catalyzed. And so if we write the rate law for this, we're looking at the breakdown of the hydrogen peroxide into water and oxygen gas. So this is a decomposition reaction. So the only reactant involved is hydrogen peroxide. So if we write the rate law, it's going to be the rate of the uncatalyzed reaction is equal to the rate constant of the uncatalyzed multiplied by the concentration of H2O2. Right? And then we have the same thing as we have the rate of the catalyzed equal to the rate constant of the catalyzed multiplied by its concentration of H2O2. And so here we can kind of see that if the rates are equal and the rates are equal to this, then we can just say, okay, well then the rate constant of the uncatalyzed multiplied by the concentration of H2O2 is going to be equal to the rate constant of the catalyzed multiplied by the concentration of H2O2. But we're told that, let's assume that the initial concentrations are the same. So if the initial concentrations are the same, then these will cancel out. And then what we end up with is the rate constant of UC of the uncatalyzed reaction is going to be equal to the rate constant of the catalyzed reaction, which makes sense. So now we can set these two together and we can use the Arrhenius equation. So what's the Arrhenius equation? The Arrhenius equation is, I'll write it over here. The rate constant is equal to the A, which is what we said was the frequency factor A, multiplied by E raised to the power of negative activation energy over the rate constant, the ideal gas law, I said rate constant, not rate constant, but the ideal gas law constant R multiplied by the temperature. So we could use this. Since the rate constant is equal to this, then we can plug that in for each, just making sure we identify uncatalyzed versus catalyzed. So in this case, we would have A times E raised to the power of the activation energy of the uncatalyzed, so we'll put UC there, divided by our T temperature of the catalyzed, because again, the temperatures are going to be different, so we have to identify or distinguish those. And then that's going to be equal to A, the frequency factor, multiplied by E raised to the power of negative EA, the activation energy, this time the catalyzed activation energy, divided by our T, but temperature here is the catalyzed temperature, which we have at 20 degrees Celsius. So now that we have these equal to each other, now look at the A. We're told to assume the frequency factor A is the same, it's constant during changes in temperature. So A can cancel out. And now we have E raised to this power is equal to E raised to this power. Okay, so what do we do here? Well, what we're going to need to do is take the natural log of both sides, because if we take the natural log of E raised to some power, the E and the natural log cancel out, and the power becomes just a regular term, right? It's no longer a power, it's just a term, okay? So then let's set this up over here. Let me go ahead and erase this. We don't need that anymore. And so here we're going to take the natural log of this. So a natural log of E, we'll just kind of put that in parentheses maybe, raised to the power of negative EA. And again, that's UC for uncatalyzed. So UC divided by R over the temperature UC, which is uncatalyzed temperature. And that's equal to the natural log of E, again, raised to the temperature of the catalyzed. So we're raised to the catalyzed part, right? So that's going to be raised to the power of the activation energy catalyzed divided by R, and then T catalyzed. As I said, when you take the natural log of E to some power, it's just the power becomes a term by itself. So basically, natural log undoes E. It's kind of like if you take a square of a square root, or the square root of a square, the square root will undo or cancel out the square, right? So it's the same thing. So this cancels out, and we're left with negative activation energy uncatalyzed divided by our T uncatalyzed. And then this cancels out, and we're left with negative EA catalyzed over RT catalyzed. Since the R value is the same, those are going to cancel out, so that cancels out. And so what we're left with is the negative of the activation energy of the uncatalyzed reaction over the temperature of the uncatalyzed reaction is equal to the negative of the activation energy of the catalyzed reaction over the temperature of the catalyzed reaction. So now all we need to do is just plug in the values that we have. Now keep in mind that the temperature of the catalyzed reaction, we need to put that into Kelvin. So the temperature 20, so this is the temperature of the catalyzed reaction is equal to 20 degrees Celsius. We're going to add 273.15 to that, and then we end up getting 293.15 Kelvin for the catalyzed temperature. And so we plug this in. So the uncatalyzed activation energy, we're told, where is it? So the uncatalyzed activation energy is 70.0 kilojoules per mole. So we'll put that in. So we have negative 70.0 kilojoules per mole divided by the temperature of the uncatalyzed. So that's what we're trying to find. Temperature of the uncatalyzed reaction. And that's going to be equal to minus the activation energy of the catalyzed reaction, which we're told is right here, 42.0 kilojoules per mole. So we're going to put 42.0, kilojoules per mole over, and then the temperature of the catalyzed, which we're told is 20 degrees Celsius, but we converted that to Kelvin. So that's going to be 293.15 Kelvin. Okay, so now all we need to do is cross multiply and solve for TUC. So we're going to multiply this times this, and we're going to then divide by this, right? So what we end up with is this times this, so we have TUC multiplied by negative 42.0 kilojoules per mole, and then that's going to be equal to these two multiplied together, so we're going to have negative 70.0 kilojoules per mole multiplied by the temperature, 293.15. Like so. So we now can then multiply these two together, divide by this, and we'll get the temperature of the uncatalyzed in terms of Kelvin, right? Here, let me just show this step just to be complete. So we'll divide by negative 42.0 kg per mole. Divide this by negative 42.0 kilojoules per mole. So then this cancels out, leaving me with the temperature of the uncatalyzed reaction is equal to this here. And then notice that the kilojoules per mole cancel out, the negatives cancel out, become positive. And so now all I need to do is multiply these together, divide by that. Here. There you go. So now you can see that better. And so when I calculate that, I get 488. Here, let me erase this now so I can get more room. So I get 400, So the temperature of the uncatalyzed reaction is equal to 488.58 Kelvin. They want this in degrees Celsius, so if we do that in degrees Celsius, we'll subtract. So that means we have to take 488.58 Kelvin minus 273.15. That's equal to the temperature of the uncatalyzed. So when we subtract this, we get 215.43 degrees Celsius, or if you want to round to the proper number sig figs, it would be just 215 degrees Celsius. And that, ladies and gentlemen, is the answer to this question, and that's how you do it. So if this video helped you out in any way, if you enjoyed this video, if this was a learning experience, then please by all means like the video, share the video, hit that like button somewhere over there. Also, do me a favor, subscribe to the channel, help me out. Also, when you do that, click on the notification bell up above. When you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question that you need help with or a topic you would like me to cover, put that down below. It would be my pleasure to help you with that. Thanks for joining me and have a great day.